All right, so today we'll finish up section 3.1. Okay, just a little bit of stuff left, and then we'll start our last section for the week, which is 4.1. So I said to you yesterday that inverse sine and regular sine cancel each other out. So, and that's true most of the time, but what I didn't tell you is they only cancel each other out if you use the right values. You got to stay between certain values. So yesterday we had these numbers we had to stay between. Today it's kind of the same thing. So if you type in something like that in the calculator, the inverse sine of the sine of, and you pick something, x, what'll end up happening, I'm going to erase this in a second, inverse sine and regular sine cancel each other out. And all that you're left with is what you originally typed in. As long as what you originally typed in is between negative 90 and 90. If you try a number that's not between negative 90 and 90, well, I'll show you what happens. Okay. Or if you're doing it in radians, negative pi over 2 to pi over 2. Okay, let's try it. So I got my calculator. I'm already in degrees. So I'm going to type the inverse sine of the sine, and then somebody give me a number between negative 90 and 90. 45. So when I hit enter, according to this chart, I should get back exactly what I started with, which in this case was what? 45. And if I hit enter, it works perfect. Inverse sine and regular sine cancel each other out. It's kind of like if you did the square root of 9 squared. Okay? If I hit enter, what would I get there? 9. I get back the same thing I started with. Square and square root cancel each other out. Sine, inverse sine, cancel each other out. Now, when I do the square root, is square root, like, does that mean you multiply? Like when you take a square root?
Divide.
Well, like if I asked you to do like this, that's multiplication, right? It's got the times symbol, 3 times 8. But if I asked you to do this, is the square root of 10, is there a time symbol in there? No, the square root of 10 is not a multiplication problem. It's a square root problem. It's its own thing, right? But there's no multiplication here, right here at all. There's no multiplication here at all, right? Some people see like those two things next to each other and they think it means you're multiplying. No, what you're really doing is you're taking the sine of whatever we did, 45 degrees. Okay? You're getting that answer and then you're plugging it into something else. So you're getting the sine of 45 degrees and then you're plugging that number into the inverse sine function. You're not doing any multiplication at all there. Just like you're not doing any multiplication at all right here. It's its own thing. It's the inverse sine function. When you put letters right next to each other, like that, xy, that definitely means multiply. When you put words next to each other, or functions, it doesn't. Okay? That doesn't mean multiplication at all. All right, so inverse sine, regular sine, let's pick another one besides 45. Let's do negative 13. So when I hit enter, what should I get this time?
Negative 13.
Yeah, because the inverse sine and the regular sine function cancel each other out. I get back what I started with. Now let's try one that's not between negative 90 and 90. Let's try like 110. So when I hit enter this time, I get an answer, but it's not the same thing I started with. It's a different answer. There's a pattern. If you kept doing these, you could probably figure out what the pattern is for the answer that it gives you. I'm not really worried about that. The point is you don't get the same answer back. Okay? Only get the same answer back between negative 90 and positive 90. What's the difference between formula 2a and 2b? They look almost the same. Joe?
Sine with negative sine or switch? reverse in problem A going down to problem B.
So which one, can you say, what's the name of that again? Yeah, so because you came in at the end. Yeah, can someone remind him, what is that one called? Inverse sign. But it's exactly what Joe said. The inverse sign and the regular sign are switched. Now, this only works if you pick a value between -1 and 1. So, regular sign and inverse sign will cancel each other out. And the answer that you get is whatever you typed in to start with, as long as you typed in something between -1 and 1. Okay, let's try that one. So we've got sine, inverse sine, and somebody give me a number I could plug in that would work. 0.5. So when I hit enter, those two things should cancel each other out, and I get back exactly what I started with, 0.5. Okay, you can try that for any number between -1 and 1, including -1 and 1. Now, if we try something not between, let's try like 1.5. This time when I hit enter, I don't even get a different answer back. I just get an error. Calculator can't even do that. So you've got to be between -1 and 1. So let's do something like -0.8. Yep, works fine. The reason it couldn't do 1.5, I can show you probably with a picture, pretty easy. I'm going to show you a graph of the sine function, and I'm going to put a line at 1.5. Then I'm going to ask you a question about it. So there's the sine function, which I can speed up a little bit. There's 1.5. Where does the blue line and the red line cross? Never. So by typing in inverse sine of 1.5, you basically just tried to figure out where these two things cross. They never do. You'll never get an answer. The highest this graph goes, I don't know if anyone can really see it, but can people tell how high the blue graph goes? 1, and how low? -1. That's where these numbers are coming from. All right, so that 1 and -1, that's not just it's not just a random number. It comes from that graph. So once we look at the graphs next week, then you can kind of make more connections with what we're doing this week. It all kind of starts to connect together. Okay. All right, let's look at this one. So this is basically just figuring out if this is true or false. So it's like a yes or no. So it says, is the inverse sine of the sine of pi over 8 equal to pi over 8? Yes or no? So first thing I like to figure out is, does this one look more like formula 2a or formula 2b? Yeah, I agree. This is 2a because the inverse is on the outside. The regular one is on the inside. So this is what we're focusing on. We have to check if the number we were given is between -pi/2 and +pi/2. Okay, so think about that on like a number line. Let's say we had 0. Over here we've got pi/2, and then symmetric on the other side, -pi/2. We don't have to know exactly where, but where would pi/8 fit into that? Roughly, just where would...
It would be less than pi/2.
Yeah, it'd be less than pi/2, because think about if you had a certain amount of money and you divide it by 8 people, it's going to be less than if you divided that money between 2 people. So it's going to be less than pi/2, but it's still going to be more than what number?
0.
Still more than 0. So it's somewhere in here. So the point is, it's between -pi/2 and pi/2. So it fits the condition it has to fit for this formula to work. So if I typed that in on a calculator, would I get pi/8? Yes, I would, because that value is between negative pi over 2 and pi over 2. So the answer there is yes. Okay, let's try this one. Okay, it's still the same setup. Inverse is on the outside, regular is on the inside. But now the question is about 3 pi over 2. Okay, so again, think of a number line. Negative pi over 2. 0 would be in the middle. Pi over 2. My question is about 3 pi over 2. Where would 3 pi over 2 compare? What would that be? Yeah.
It would be a little bit less because that's 60 degrees, if I remember correctly, or is it 30?
Well, in degrees, 3 pi over 2 would be 270.
Oh,
Yeah, 30 would be pi over 6. But you don't even have to think about it in degrees. If you know you have to be less than pi over 2, this is triple pi over 2.
Yes, it's over.
It's over, right? This is pi over 2 tripled. It's too big. So the question here, if you type that in, will you get 3 pi over 2? No, you won't. And when I converted it to degrees and told you it was 270, well, that also tells you, no, it's way over. It had to be a maximum of 90. All right, let's try this one. Is this formula more like 2a or formula 2b? Yeah, now the inverse is on the inside. So when the inverse is on the inside, for the formula to work, in my head, what I picture is how high and low the graph goes, okay? Because I'm used to graphing it. But since we haven't really done that, you just have to remember -1 to 1. Are we between -1 and 1 here? Joe?
No, no.
No. So this is the one where if you type it in, you won't even get an answer back. You're basically trying to find where two graphs cross and they never do. Okay, so that's impossible to solve. How about this one? The sine of the inverse sine of 0.6. If I type that in, will I get 0.6?
Yeah.
Yep, how come?
It's less than 1.
It's less than 1, but it's greater than
Negative.
-1. You got to be between -1 and 1, and we are. The only other way you could see a question like this written would be if it said, let me just write it like this. Erase this, erase that, and put simplify. If I write this expression down and I say simplify, don't put yes. That doesn't really answer the question. If it says simplify, you have to tell me the answer. So what is the sine of the inverse sine of 0.6? Joe?
0.6.
The answer now would be 0.6, not yes. Okay. Any question on that? Yeah.
What if it's like not, like what if it's like over 1?
Like when you, yeah. If I have you simplify it, I'll probably give you one that you can do. Yeah. If I did give you one you can't do, you could just write not possible. But I'm probably going to give you one you can do because I want to see if you know how to do it. And if I give you one that's impossible, I can't really tell if you know what you're doing. So I'll give you one you can do. All right. So any question on that idea, just the difference there? I think the ones in the homework are set up like this, yes or no. All right. So we'll look at the same idea for inverse cosine and inverse tangent. Okay, so let's think about this one. The inverse cosine of the cosine of x. Those two things will cancel out, and you'll get back exactly what you typed in, as long as x is between two numbers. Let's go back and look at what they were for sine. When the inverse is on the outside, the two numbers we have to be between, those are the two numbers that came up yesterday. Does anybody remember what the two numbers we had to be between for inverse cosine were yesterday? Yep.
0 and 80.
And that's exactly what they are here. That formula works if you're between 0 and 180. I'm not going to type in examples on the calculator, but if if you want to try one, it'll work between 0 and 180. Or 0 and pi if you're doing radians. Now, when we switch it, the cosine of the inverse cosine, now the inverse is on the inside, this has to do with how high and low the graph goes. I don't know if I've shown you the graph of cosine yet, but I'll show it to you right now. I think you'll be able to tell me how high and low it goes. How high and low does that graph go? The one in black. 1 in the lowest? Yeah, it's exactly the same as sine. In fact, it's just sine kind of bumped to the left a little bit. That's all that cosine is, visually. Just move it to the left. So that 1 and -1 is exactly the same. This is the problem where if you type in something bigger than 1 or smaller than -1, you'll get an error. It won't even work. Okay, reason it won't work, same idea as tell me where the red line and the black wave cross. They don't. Okay, so let's just try a couple with cosine. Okay. Cosine of inverse cosine. So first thing I'm going to check out is, does it look like formula 4a or 4b? Scott?
B.
B, yep. So if it's 4b, we have to be between -1 and 1. Is the number they're giving me here between those two?
Yeah.
Yep, so that would work. That's fine. Let's look at this one. Now the inverse is moved to the outside. Regular cosine is on the inside. Those two will cancel out as long as they picked a number between what it had to be between, 0 and 180. So Eric, is that one going to work here?
Yes.
How come?
Oh wait, no.
No.
No, it's not. Because it's not between 0 and 180.
Yeah, it's not between 0 and 180. You can type it in, you'll get an answer. It's not the one that's going to give you an error, but you're not going to get 210. You're going to get something different. All right, so the answer here is no. So you're always supposed to, whenever you do inverse cosine, right, because that's what's on the outside, you're taking the inverse cosine of something. Well, inverse cosine has to be between 0 and 180. You're not going to get an answer of 210. Okay, that's like you looked up a different answer on that sheet I gave you yesterday, and you picked a different one. Okay, you won't ever get that on the calculator.
Will you ever put the 210 in the parentheses and then have a different answer outside?
No, we're just checking to see if the number that's here is the same as the number there. Yeah. Okay, and tangent. All right. So when the inverse is on the outside, the value you plug in has to be between the two numbers we talked about yesterday. Does anybody remember the numbers for tangent that we talked about yesterday? Yep.
-90 to 90.
-90 to 90. That sounds like sine to me, but there's one small difference. What's the small difference? Yep.
Has to be greater than -90. It has to be less than 90.
Exactly. There's no equal to's. So it can't equal 90. And the reason, if you look at your chart, look at 90 under the tangent column, it's undefined. Okay. So this formula works as long as you plug in a number between -90 and 90. And when I say between, I mean between. You can't use -90 and 90. When you move the inverse to the inside, this has to do with how high and low the graph goes. Now, the graph of tangent looks totally different than the other ones. So it's not confusing. I'm going to take away the other ones. And I'm just going to type in tangent. And I want you to see if you can tell me how high and low the graph goes. So there's a pattern to it, right? But it's not a wave. Anyone have a guess how high and low this graph goes? Yeah, it goes infinitely high. You know, if you're thinking, well, maybe if I zoom out, it'll stop somewhere. If you look at that, that's kind of confusing because this is where the calculator is having a little trouble. It shouldn't be stopping. And it's because once it gets too steep, it almost goes straight up. The calculator can't draw things that go straight up. If I shut this off, it might drew it faster, but it still didn't draw it the way it should. If you look, actually, if you look at this, it looks really weird. If you zoom in, to me, it looks like it's only going up to 1, 2. It's stopping at the second mark. Well, if I go back to the way I am here, now look at it. Just by zooming back in, now it's stopping at the 4th mark. So the calculator is having a little trouble, and really it should go up and down forever. So for 6b, the formula always works, no matter what. So, okay. Another way to think about it visually, if here's your graph of tangent, it looks something like that. That goes up forever, and that goes down forever. Is there anywhere that I could put a horizontal line where it would never hit tangent? No, it's going to hit it everywhere. It's not like the wave, like this. It's not like when you have the wave where if you move it high enough, it doesn't hit it. Tangent goes up forever. So no matter where you put it, you're always going to hit it. So you're always going to get an answer. We don't study the graph of tangent in this class too much. Since it's a half-year class, we really focus on sine and cosine. If it was a full-year class, then we'd spend like another week looking at a little more complicated graphs. But tangent, we won't look at. Okay. So let's just do one tangent problem. The tangent of the inverse tangent of 30.4. If I type that in, will I get 30.4? Yeah, this is the one, this is formula 6b. When inverse is on the inside, doesn't matter what you type in. It always works. You don't have to know that this formula is 6b or that this one is 6a. That's what they're called in your book. So if you want to look them up, that's how they label them. But you don't have to know 6a, 6b, those numbers. You just have to know that part of it right there. Okay, call it whatever you want. Okay, so that's the end of section 3.1. So the last section we're going to look at this week is 4.1. And sometimes you look at it a little bit in geometry. You do Sakatoa. Does anybody know what I'm talking about with that? I'm sure. So if you're not sure, that's okay. That's why you're here. I'm sure. But it is something some people might have done in geometry a little bit. So we're going to be looking at right triangles. Everything involving a triangle from this point forward for this week is all going to be right triangles. Okay, what does it mean if you have a right triangle? What's special about it? It's a triangle. It's got 3 sides, but so is this. There's a triangle, but that's not a right triangle. Corey? Yeah, it has a 90-degree angle. Okay, and when you have a triangle with a 90-degree angle, then we also have something else. We also have what's called a hypotenuse. Okay, the definition of a hypotenuse is the side opposite the 90. If you don't have a 90, you don't have a hypotenuse. And then the 2 shorter sides that aren't the hypotenuse, those are your legs. In a right triangle, we have one angle that's a 90, but then we have a couple other angles here that are acute. What does it mean if an angle is acute? Yeah?
Less than 90.
Okay, less than 90. And one other thing. I could give you an angle that's less than 90, but it's not acute. Anybody know what I'm getting at?
0.
True, 0 would be an angle that's less than 90, but it's not acute because the angle 0, it doesn't even exist really.
Wait, is it like all angles equal to 90?
Not everything. It has to be smaller than 90, but it has to be more than, it's got to be more than 0. So it can't be 0. It also can't be negative. Negative angles are not acute. Okay? Acute has to be between 0 and 90. That's the definition. Okay. When we work with right triangles, we're going to use a theorem quite a bit. Specifically having to do with the sides. And can anyone tell me what that theorem is? You know what the Pythagorean theorem is? Yep.
A squared plus b squared equals c squared.
Okay, so it's a squared plus b squared equals c squared. Now, in my triangle, I don't have any a, b's, and c's. So, can you tell me what's a, what's b, and what's c?
A and b are the two legs.
Yep.
And c is the hypotenuse.
Exactly. So the Pythagorean theorem says that if you square the two legs and add them up, it'll equal the hypotenuse squared. Usually we use the letters a, b, c, but you could use XQP, whatever you want to use. But that's the idea. Leg squared plus leg squared equals hypotenuse squared. Alright, so when we define the trig functions, we're going to go through them just like we did with unit circle trig. I'm going to show you what the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent are. But in the definitions, I'm going to use these two terms. And hypotenuse. Hypotenuse, that's an easy one. It's the one across from the 90. But I have to describe what the terms opposite and adjacent mean. Does anybody know what those two words mean? Like if we talk about opposite versus adjacent? I don't think they could explain to me what they mean. Yep.
Adjacent is like touching your own on the same side and opposite is across.
Yeah, so opposite is across, it's farthest away. Adjacent is the one that's right next to it. But what we have to be careful about is they are what we call relative terms. It's kind of like left and right. It depends on which way you're facing, which way is left and which way is right. For me, left is the door and right is the windows. For you, it's the opposite. So it's the same with these two terms. Opposite and adjacent depend on your perspective. And the perspective is going to be shown by putting a triangle and the Greek letter theta somewhere. Theta is your perspective. So if you were standing at theta, that side would be opposite. It's the side that if you just erased this side, wouldn't have anything to do with that angle over there at all. Adjacent is the side that's right next to your angle. And if you're saying, well, aren't there two? Yeah, but one of them is the hypotenuse. So it's the side that's right next to your angle that's not the hypotenuse. It's the side that if you erased it, I can't erase it, but if I could erase it, I wouldn't even have an angle there anymore. It would look just like this. Now it's just open on the bottom, there's no angle. Now, if I take the same triangle and just make a copy of it, and I move my perspective here, okay, so now you're standing in a different spot. There's one side that stays the same. Which side won't change? Joe?
Hypotenuse.
Hypotenuse is always across from the 90. But opposite and adjacent will switch. Opposite is the side that's farthest away, doesn't touch the angle at all. Adjacent is the side that's next to your angle. Okay, so if you want to write that down, it's up to you. Opposite, the side in a triangle that is not part of the angle at all. If you erased it, wouldn't even matter. And adjacent is the side in a triangle that is one of the sides of the angle that we're talking about. If you erased it, you wouldn't have an angle anymore. Those are your terms, opposite and adjacent. Again, I already explained to you, bless you, Okay. Explain to you how they're relative terms. Okay, so what we're going to do now is I'm going to define all 6 trig functions using the words opposite, adjacent, and hypotenuse. Now, when we did it with unit circles, we used x and y. Well, and hypotenuse. This is going to be exactly the same thing. And I'll try to make the connection between this and what we did last week. All right, so sine, I'm going to put in red what we had last week below it. You don't have to write the part in red, just what's in black right there. But last week, sine was y over r. Now, if r was 1, it was just y. Okay. Cosine was x over r. And again, if r was 1, cosine just came out to x. And tangent. Does anyone remember what the formula was for tangent last week? It was y over x. Okay, what I'm claiming is that what we did last week and what we're doing this week is the exact same thing. And I'm going to show you why. So if I had a circle, okay, that's how we did unit circles last week. Made a circle, put a point on the circle, make a triangle. There's your perspective right there. Pretend you're standing right near the origin. What is this side called, since it's the distance from the center of the circle to the edge? Yeah, it's my radius. Sometimes it was 1, most of the time it was last week, but we also looked at examples where it wasn't. How about the length of the bottom side? What do you call that, since it's the horizontal? Well, what did we call it last week? X. And what did we call the height? Y. So let's look at how this kind of ties in. So last week, sine was y over r. Y over r. Well, from the perspective of theta, since y is the side that's farthest away, what's another name for y that we learned this week? Y is opposite. And r is across from the 90, so we call that side hypotenuse. Across from the 90. So r is a hypotenuse, y is opposite, but look what happens. Y over r is the same as opposite over hypotenuse. It's just giving a different name to the exact same thing. That's exactly what we did last week. Tangent was y over x. Well, y is opposite, x is adjacent. Opposite over adjacent is tangent. We're just not going to call it y and x anymore. We're going to call it opposite and adjacent. So it's really the same thing. And now once we had the 3 on the left, what did we do to get the 3 on the right? Yep, flip them. It's exactly the same thing. So your cosecant is hypotenuse over opposite. Your secant is hypotenuse over adjacent. And your cotangent is adjacent over opposite. Okay, I was running out of room, so I just started abbreviating hypotenuse, opposite, and adjacent. So there's a trick to remembering the trig functions, and that's what I was mentioning earlier. Okay, if you look at sine, sine is opposite over hypotenuse. So you got that part. What's cosine? That's adjacent over hypotenuse. And tangent is what's tangent, Chris?
Really realize what you're doing. Opposite over adjacent.
Tangent is opposite over adjacent. You got it.
It's not this fixed.
Just try to pay attention now.
It's like a
So, Sakatoa. Alright, if you read that off, that's kind of how you can remember it. Sakatoa, well, if you remember how to spell it, that'll help you to try to remember sine, cosine, and tangent. Before, I had somebody mention the way they remember it is Sacagawea. Not quite, it's Sakatoa. But if Sacagawea helps you, you go with that. I'm not sure how she's going to help you. And then if you try it with the other three, it doesn't really help at all. Cosecant is hypotenuse over opposite. Secant is hypotenuse over adjacent. And cotangent is adjacent over opposite. So, Choshokao.
I like that better.
That's my favorite Chinese food.
So if you want to go with Choshokao, there you go. Most people that have done this go with the Sakatoa. Whatever works. Alright. So let's practice a problem where they give you a triangle and they want you to find all 6 trig functions. Now, before we start, there's something we should do. We could do some of these right now, but we're missing something. What are we missing that we're going to need in at least 4 out of 6 of the problems on the board? Yeah?
Hypotenuse.
We're missing the hypotenuse. So, how can we figure it out before we start? Yeah? Yeah, we can use the Pythagorean theorem. So 3 squared plus 4 squared equals, you can call the hypotenuse whatever you want, c squared. What's 3 squared plus 4 squared?
25.
So I get 25. But I don't want the hypotenuse squared, I just want the hypotenuse. So what do I do on both sides?
Square root.
Yep, take the square root. Take the square root. So the hypotenuse is how long? 5. So the fact that it worked out nice is good, because if it didn't, like let's say it was the square root of 26. Well, now we could end up with square roots in the final answers, and whenever you have a square root, you have to make sure that you never leave it where? Yeah? In the denominator. You can never have a square root in the bottom. Not going to have to worry about that here because the square root came out nice. If it doesn't, you have to deal with the square root in the bottom. All right, so let's go through all 6. So how about Derek? Can you tell me what my sign would be?
It would be 4/5.
Yep. So it's opposite over hypotenuse, which is 4/5. Mike, how about my cosine?
3/5.
Yep. Adjacent over hypotenuse. So 3/5. And Justin, my tangent?
5/3.
So what's the definition for tangent again?
Opposite over adjacent.
Opposite. So 5 is the hypotenuse, because it's across from the 90.
4/3.
4/3, yep. So we got 4/3. And now that we have the 3 on the left, the 3 on the right are easy, because all we got to do is take those and flip them. So 5/4, 5/3, and 3/4. So we just found all 6 trig functions. What we never found, though, is how big is that angle? Is it 40 degrees, 50 degrees, 70? How big is it? We don't know. Any one of these 6 pieces of information I could use. Like if you told me the sine is 4/5, I could tell you what the angle is. I could solve for the angle somehow. And what did we learn earlier? That if anytime you want to solve for an angle, what do you use to do it? anytime you want to find an angle, what do you always have to use? Well, Pythagorean theorem is to find sides. So we use that for sides. How would you get rid of sine here and get theta by itself?
Oh, inverse sign.
Inverse sine, exactly. If you were dealing with this one and you wanted to get rid of that, so it said theta equals, you would take the inverse sine of 4/5, and that would tell you how big that angle is. Or you could take the inverse cosine of 3/5, or the inverse tangent of 4/3. You'd get the same answer no matter which one you did. That would tell you how big the angle is. Let's just try it. So let's see how big it is. So the sides come out nice, 3, 4, 5. The angle does not. So again, you don't have to find the angle, but if you wanted to know what it is, it's 53.13. Or do the inverse cosine of 3/5. You're going to get exactly the same answer. Or inverse tangent of 4/3. Okay, any one of those pieces of information could tell me how big the angle is. That we're going to look at more tomorrow. Any questions on just what we did there? Right, so on the test, some people get confused with that. There's a difference between just finding the trig function, which is what all those fractions are, and then taking it one step further and actually finding out the angle. Okay, so don't get confused with that. If it asks for a trig function, you're just writing a fraction. If it asks for an angle, then you're going to use your calculator, and we'll do that more tomorrow. Complementary angles. Anyone remember what those are?
Is it like 90? Like supplementary is that 180?
Something about 90. Yeah, what about 90 though?
The sum of two angles?
The sum of two angles that add up to 90 degrees. Okay, so that's what it means if their angles are complementary. So I wrote on the board that the two acute angles in a right triangle, here and here, I'm saying that those are always going to be complementary. Why? Why would the two small angles in a right triangle always have to be complementary? Yeah?
Because it has to add up to 180.
Yeah, all the angles have to add up to 180.
And the other angle's 90.
Yeah, and you've already used up 90 right there. So if they're going to add up to 180, then those two also have to add up to 90. So the two small angles are always complementary. So keep that in mind. So we have 6 functions: sine, cosine, tangent, cosecant, secant, and cotangent. And the way I have them paired up across from each other here, they're reciprocals. You flip one to get the other. Okay? That's one way to pair them up. Another way to pair them up is like that. Pairing them like this, they're called cofunctions. And if you pronounce them, I think it's pretty clear why. Sine, cosine. Secant, cosecant. Tangent, cotangent. Tangent and cotangent happen to be the same. They're cofunctions and they're reciprocals. But the other two are not. So a cofunction is when you just take a trig function, like sine, secant, or tangent, and put the word co in front of it. That's the cofunction. Okay, this would be kind of a weird question, but what if I asked you, what's the cofunction for cosine?
Inverse.
So for sine, its cofunction is cosine. So for cosine, its cofunction would be sine. Yeah, you wouldn't say cosine. It's kind of weird. But yeah, the cofunction of cosine is sine, and sine is cosine. They're paired together. Okay? Same with secant, cosecant, tangent, and cotangent. So we're going to look at this triangle. And this is how you kind of label a generic triangle, if you don't know any of the sides and any of the angles, English letters are usually used for the sides, and Greek letters are usually used for the angles. That's the Greek letter alpha, and that's the Greek letter beta. And it's important where you put them. Usually you put alpha across from A, so A and alpha should be opposite, so should B and beta. And the reason why we do that is it makes it clear, like if you ask me, I don't understand where you got beta, I know you're talking about an angle. Versus if you said to me, I don't know how you're getting A, I know you're talking about a side. So we always just use Greek letters for angles, lowercase English letters for sides. Some books use like lowercase English letters for sides and capital English letters for angles. Then that gets kind of confusing because if you say to me, how do you get B? Then I have to be like, do you mean capital B or small b? Which one are you talking about? This kind of avoids that. All right, so let's, we can label this side C if you want to. That's the hypotenuse. Let's find the sine of alpha. So it's not going to be numbers here, it's just going to be letters. So sine is opposite over hypotenuse. What side is opposite alpha? A. And what's the hypotenuse? Which side? B. Is B across from a 90?
C.
C. C is the side across from the 90. So the sine of alpha would be A divided by C. Nothing fancy. What's the cofunction for sine? Cosine. All right, so let's put that down. And what angle is complementary in that diagram to alpha? So what's the angle that adds up with alpha to give you 90?
B.
Well, B's a side.
Oh, like the top angle.
The top angle, yep, which is beta.
Oh.
So remember, the two acute angles in a right triangle are complementary. It doesn't matter what you call them. Alpha and beta, John and Sarah, whatever. The two acute angles always add up to 90. So angle that adds up to 90 with alpha, beta. Let's figure out what that one is. So I'm using the cofunction, and I'm using the complement of the first angle. Okay, cosine is adjacent over hypotenuse. Dylan, what side is adjacent to beta?
A.
A. And what's the hypotenuse?
C.
C. If you compare what we got before to what we just got now, how do they compare?
They didn't split.
They're what?
They're still the same.
Yeah, they're the same, right? Sine, cosine, those are cofunctions. Alpha, beta, complementary angles. Let's try it one more time and see if that happens. Let's do tangent. All right, so tangent is opposite over adjacent. All right, so what side is opposite alpha? A. And what side is adjacent to alpha? B. A over B. Now, the way I'm going to set up the other one is I'm going to find the cofunction and then the complement. So what's the cofunction for tangent? Joe?
Cotangent.
Cotangent. And what angle is complementary to alpha?
Beta.
Beta. Let's see what happens. So again, the key, the way I set this up is I pick the cofunction and the complement. And see what the answer is. So cotangent is adjacent over hypotenuse. So, I'm sorry, adjacent over opposite. So there's beta. What side is right next to the one that I circled?
A.
A. That's adjacent. And what side is opposite the one I circled? B. It came out exactly the same again. And that's not a coincidence. That will always happen. And that's called the complementary angle theorem. Okay, which, very simply, that's the whole theorem. If you have cofunctions, so any of the pairs I just showed you, sine, cosine, secant, cosecant, tangent, cotangent, if you have one of those pairs, and you're dealing with angles that are complementary, they come out exactly the same. So cofunctions of complementary angles are the same. Okay, so let's look at these three and see if we can figure out something else that would come out the same as it. Except this time we're going to do it with actual numbers. So I've got the sine of 30. First thing I need is the cofunction. So for the top example, what's the cofunction for sine?
Cosine.
Cosine. So I'm going to start with cosine. And now I need something complementary to the angle they gave me. What's complementary to 30? Yeah? 60. So the sine of 30 would come out exactly the same as the cosine of 60. And that's super easy to prove. Sine of 30, 0.5. Cosine 60, 0.5. They come out exactly the same. Let's try this one. Tangent of 15. Anyone think they could tell me what that would come out the same as? So not the answer for tangent of 15, just something else that would be the same as it. Yeah?
Cotangent of 75.
75, yep. The tangent of 15 would be exactly the same as the cotangent of 75. Why is that useful to know? I'm going to show you in 1 second. It makes a special trick happen. How about the secant of 40? What would that be the same as? Think of the cofunction. Think of the complement. Yeah? The secant. So you said 50, and what was the function you said? Cosecant. So cosecant of 50. So doing this still doesn't tell me what the answer is. If you ask me what the answer of tangent of 15 is, I still have no idea. It's not a nice number I can do in my head. But I know that it comes out the same as the cotangent of 75. And that's going to help me to do something like this. So this problem is asking me to find the sine of 15 divided by the cosine of 75. Okay, off the top of my head, I have no idea what the sine of 15 is. I don't know. It's a decimal. It's not a nice answer. Same with cosine 75. But sine, cosine, okay, those are cofunctions. 15, 75. What are 15 and 75? What kind of angles? Complementary. I have cofunctions of complementary angles. So what does that mean about the top? If you figured out what's in the top and you figured out what's in the bottom, how would those two things compare to each other? Joe?
The same number.
They're the same thing. I don't know what the top is, I don't know what the bottom is, but I know they're the same thing. So if I divide two things that are equal, I get one. Doesn't matter what they are, but I know I get one. So that's where that trick comes in handy. Alright, how about something like this one? The tangent of 12 minus the cotangent of 78. This one's even worse. I have no idea what the tangent of 12 is. And I have no idea what the cotangent of 78 is. But tangent, cotangent, those are cofunctions. 12 plus 78 is 90. So if I compare the first thing to the second thing I'm subtracting, how do those two things compare to each other? they're equal. And what happens if you subtract two things that are the same?
0.
You get 0. Okay, you get 0. Now, this has to be set up very special to work. If I change 78 to 79, the whole thing's out the window. You can't do it. You got to use a calculator now. Or if I change cotangent to something different, like secant, can't do it. Okay? Has to be cofunctions, has to be complementary. So it works with subtraction. It works with division. How about addition? If you add two things that are the same, do you always get the same answer? No. If you subtract two things that are the same, you get 0. If you add two things that are the same, you get that thing doubled. So that doesn't work. How about multiplication? If you divide two things that are the same, you get 1. But if you multiply two things that are the same, do you get the same thing? No. Joe?
Should you put a square around one of them?
You'd get that thing squared. So, again, what would that be? It's different for every number you square. So it doesn't really work with multiplication or subtraction. And it pretty much always comes out to 0 or 1. The only way it could come out to something different is if they did something like that. Well, now it's 1 times 4. Okay, then it could come out to 4. But other than doing something like that, it always comes out to 0 or 1. Okay, any questions on that? So that's the first part of section 4.1. So the first part of the homework, those are all yes or no questions based off the first thing we did, page 187. 46 to 51, 53 to 55 all. And then page 255, that's the last part we just did with the triangles, 9 to 21 odd. Okay, so tomorrow we'll finish up everything for the week. Thursday will be a review day, and then on Friday we'll have our test.